Welcome to episode 1 of Volatile Memory Analysis of Stuxnet. My name is Ben Rogers, and I am doing this for a capstone project on behalf of Champlain College. Two things to note right off the bat are that I'm going to be working in 2 terminal windows, simply because when working with some of the commands, it's easier to look back at data from previous commands and using that to enter new commands. Just makes life a little bit easier. The second thing to note is I'm working off a folder on the desktop which contains my volatility program as well as the memory image we are going to be using. So, now that that's out of the way, the very first thing that should be done when getting an image is you should really run a command called image info. So we're going to go ahead and do that. Just to note, I'm sitting in the volatility folder inside of the forensics folder on the desktop. That is where you have to be to run all of the Python scripts, including the main vol.py Python script. Moving on, so what we're going to do here is a simple command that just specifies, and remember, tab complete is your friend. Sorry. Volume was on. You don't need to hear my errors. So, we're basically switching into the memory image folder to look at the memory image we have. Again, mine is a virtual memory image. I took it from a virtual machine, which makes memory capture very easy because virtual machines lock the memory away as separate files, so there's no real extracting that has to go on. You can simply take the vmem file away from the directory where the virtual machine is in, and you have essentially imaged RAM. So here's a command. So what this gives us is, it essentially gives us the profile that the RAM was in when it got imaged. So what we're looking at here is a Windows XP Service Pack 3 image that was taken 2011-06-03 at 4/31/36. Now, the reason we do this is, one, to verify that the image isn't corrupted. The second reason is there are some commands, we won't be dealing with any of them today, but there are several commands that require a profile to be added to the command in order for it to run correctly. In this case, we would end up using a profile switch, which I will explain when we get there, but it will end up using this string after the profile switch so that the program can understand how to look at the data. So when dealing with malware, the most likely symptom is going to be some sort of process that shouldn't be running, that is. This can be obfuscated in several ways. Stuxnet does it in its own way. So the easiest way to look at this is to, again, use our volatility script. Volatility is a great tool for analyzing memory. Again, it takes a little bit of getting used to, but it is free, it's downloadable, and it's very powerful with the information it can provide you. So again, the most likely symptom of most malware infections, including Stuxnet, is a process or several processes that should not be running. So the first command we're going to run is a process tree. What this does is essentially looks at all the running processes at the time the memory was captured. So what this allows us to do is go ahead and look at that in a controlled environment in order to figure out what doesn't fit. Now, as we can see from this output, this isn't really that well organized. The time is sort of looping down into the next line. At least there's headers, so we know the name of the process as well as the offset that it was running on. But there's another command which essentially does the same thing, called process list. Process list organizes the data a little better. It's a little easier to look at, so I'm going to go ahead and run that in the above window, and there we go. As we can see, it's organized a little better. It spaces it out. It actually identifies the offset as an offset, whereas the other one does not. So, moving on. What we have here is the list of processes that was running when this was captured, and this is a machine that is infected with Stuxnet. So, I know from research that Stuxnet starts two executables under the name lsass.exe. I'm going to be referring to that as LSASS for the rest of the video. As we can see, there is an instance of it right here. Now, this process is the local security authentication server. What it does is it verifies the validity of user logons to your PC. It also generates other processes responsible for authenticating the user's logon service. It essentially is the key to the castle. It lets you go ahead and look at your files, your programs. It allows you to make modifications to the system. If the authentication is successful, this process generates the access token, which is used to launch the initial shell that the user is able to do any commands, run any processes, install any programs, anything of the sort. So, after researching this, we've learned that LSASS should only appear in a process list once. Well, when we start going through the process list that we just called forward, we see that as we scroll down, again, here are some of my VM applications that are running. As we scroll down, there are two extra LSASs that appear to be running with the process ID of 868 and 1928. So we have three lsass.exes. Now, the problem is identifying which one is the legitimate executable and which are the rogue executables. So, the first command we're going to run to try to decipher which is a rogue executable and which is the actual executable is we are going to try to identify which users have access to the executable. So the first thing we're going to do is I'm going to use the getSIDS command. This is going to show us who has access to that program and who is using it. I'm also going to be using the p-switch right here. That is going to allow us to cut the output to only the process IDs we are looking for. So the process IDs we are looking for are 680, 1928, and 868. And there we go. So what this tells us is that process IDs 680, 868, and 1928 all have the same access. It is being used by local system, administrators, everyone, and authenticated users. So as we run into a problem right now where we can't really tell the difference between the two. The executables appear to be the same. They appear to be accessed by the same people. There's no real differentiating factors right now. So in order to, after researching lsass.exe, what we are able to find is that it is a program which runs at a higher base priority than the normal Windows priority. Most executables that run in Windows start with a base priority of 8. LSASX, or LSAS, which is used to launch the initial shell, has a higher base priority because it needs to run before anything else can run. That means that its base priority should be higher than 8. In Windows XP, it runs at a priority of 9. So, in order for us to get this, we have to go ahead and open up a volatility shell within the memory image. This will allow us to get more specific data, as well as output that to a format that we are more able to understand. So, the way we do this is we go ahead and we open up a volatility shell. As you can see, 3 little arrows appear, and that means it's time to start typing your request. So, I'm going to go silent for a little while I type this. It's very specific. If you're following along at home and you have an image of a volatile memory image of Stuxnet, feel free to follow along while I type this, but I will be back with you in a moment. Okay, so assuming that we get no errors in the typing of this command, which we may, in which case I will fix it, but it's always a good learning experience to see syntax errors in commands such as these. So what we're saying is, for the processes in Windows 32, in the pslist command, take the process IDs of 680, 868, and 1928, and then print the process ID and the priority number of that process in the following format. That's what the 3 lines say. So let's go ahead and see if this executes. Again, we have an issue. The error appears to be in the first line, so I'm gonna go, yep. Again, okay. Apparently fat-fingered one of the commands. So let's try this again. Luckily, it caches the commands. There we go. So, as we can see, it has printed the process ID and the priority number. So it appears that 680, which has a priority number of 9, which from, as I stated earlier, and also the research that I performed, should be the base priority of the legitimate lsas.exe. The other 2, process ID 868 and 1928, appear to be of lower priority numbers, meaning they were started after the initial shell was launched, meaning they are the rogue executables started by Stuxnet. So, that is it for this video. Again, what we did was we went through image info, what that can tell us, the process listings, and then how to identify which executables are indeed the rogue executables from that process list. Thank you. There will be more videos coming soon where we dig into what these executables are, what they're linked to, and what exactly they're doing. So stay tuned, thank you for watching, and good day.